So in the last video we just finished talking about, we introduced the idea of a random variable, and we said that a random variable will take on the different values with different probabilities. So we're going to review that again right here in example 5. We return to the coin tossing experiment in example 1. In the left column of table 1 we listed the 8 possible outcomes for this experiment. Do they show us this again? No. So let's quickly go back and see it again. So here it is, the 8 different possibilities, and this was the random variable which counted the number of heads. If we assume the coin is fair, then each of these 8 outcomes will be equally likely. Remember, we called that a uniform probability model, so that each outcome will have probability of 1/8 of occurring. From the right column of table 1, we see that x takes on the value 2 for 3 of these sample points. Thus, the probability that x equals 2 will be 3/8. And this is how we write that. Now, this might look confusing, and I like to put, although I can't do it in this text, I like to put right here a quotation mark, and right here a quotation mark, to indicate that this is actually the name of an event, because I like to remember that when we ask for probabilities, we're asking for probabilities of events. So this looks very confusing, but if you were able to put quotation mark here, here and here, then you'd say the event called x equals 2. What event is that? The event called x equals 2 is this subset of the sample space. Here's the sample space. The whole thing is the sample space. This subset of the sample space is the event x equals 2. So if you put the quotation marks around it, then you're talking about the name of some event, the event called x equals 2, which contains 3 elements, all equally likely, so the probability is 3/8. But nobody does that, so they just write it like this. The probability that x equals 2 equals 3/8. Okay? Similarly, table 1 shows that the probability that x equals 0 is 1/8, because there's only one case where that happens, and that's when you have all tails, TTT. And this one is also 3/8, because there are 2 cases for that. And this is, right, 2 cases up here, right, when x equals 1. Right, this is h, just 1h, 1h, 1h. So you can say, where can I put the 1h? So I could put it in the first place, in the second place, or the third place. And that tells you that there are only 3 possibilities, so there's 3. So we can say the probability that x equals 1 is 3/8, the probability that x equals 0 is 1/8, the probability that x equals 3 is also 1/8, and the probability that x equals 2 is 3/8. Okay, so we're going to use this notation. You're going to see this notation often. Okay, we can also ask this question. So again, I guess I would put quotation marks around it, but what does this mean? The probability that x is less than or equal to 2. What does that mean? X is what? The number of heads. X was defined to be the number of heads, right? So let x, introduce the random variable x to denote the number of heads. Okay? So this says the probability that x is less than or equal to 2 means that the number of heads is less than or equal to 2. The number of heads is less than or equal to 2 means that the number of heads is what? Either 0 or 1 or 2. Less than or equal to 2 is either 0 or 1 or 2. Now answer the question, why were they able to put plus here? So why can they go from here and get this to plus it? So let's review that, because we've talked about it before. So we start with this, the probability that, whoops, how do I get rid of that? Probability that x is less than or equal to 2. What does that mean? That means that the probability that x is equal to 0 or equal to 1 or equal to 2. That's just the meaning of less than or equal to. Now, or can change to union. Actually, I should put... Okay, so I put the union of the event that x equals 0, union x equals 1, union the event that x equals 2. Actually, I should put those quotes around here if I want to be consistent, but it's too much trouble to type it, so I'll just leave it here. Okay, so or becomes union. These should all have the quotes. But so this becomes the union of these three events. This is the event that x equals 3. This is the event that x equals 1. This is the event that x equals 2. Okay, now why can I change these from union to plus? Because these are all mutually exclusive, right? If x equals 0, then x cannot equal 1. In other words, why not? Because x equals 0 means that you got no heads, and that doesn't happen if you got one head, and vice versa, right? So these are mutually exclusive. So then I can change union to plus, which is what they had there. So they have this, this, and this. And we already figured out what these are. X equals 0 was 1/8. X equals 1 was 3/8. X equals 2 was also 3/8. So this is what we get. So we get 7/8. So the probability that x is less than or equal to 2 is equal to 7/8. The probability that x is greater than 2, what can we do there? We could figure out what this means using this kind of calculation, but we can also, we have another rule, which was this rule, right? The probability of e prime equals 1 minus the probability of e, right? Remember this? E prime here and e here. So if we want to figure this out, we're allowed to use, call this e, or I'm sorry, call this e prime if we want to, if we can identify what we mean by the e related to this e prime, we're allowed to put that here. So what does this mean? This is what? X is greater than 2. What's the opposite of x being greater than 2? X is less than or equal to 2. So the probability that x is greater than 2 is 1 minus the probability that x is less than or equal to 2. But we just figured out what this was. This was 7/8. So the probability that x is greater than 2 means 1 minus 7/8, which is 1/8, which of course we knew because that x is greater than 2 means x is equal to 3, and the probability that x is equal to 3 means the probability that you get exactly 3 heads, and that is 1/8. And actually that's what they say right here. Okay, so we explored this kind of notation, x equals 2, x equals 1, and so on. Then we also extended it a little bit. We said x is less than or equal to 2. What does that mean? That's actually the union of other values of, or we can view it as the union of x equals 1, x equals 2, and x equals 0, x equals 1, and x equals 2. And we saw that we can, or can become union, and these are disjoint, so we can add. Okay, now let's go back. Let's go to back to a different experiment. Remember, this was tossing 2 dice, and this is the sample space, right? There are 6 by 6, in other words, 36 different possible outcomes. Okay, so let x denote the sum of the numbers tossed with 2 fair dice. Find the probability. So we said there are 36 outcomes, but with any particular outcome, can I do this? So like with this outcome, there's a number associated with the number that we're associating is the sum. So we said a random variable associates a number with each outcome. So here we have a random variable which associates the sum with this outcome. So the sum is 5. Here the sum is 9. Okay? So we say let x denote the sum of the numbers tossed with 2 fair dice. Find the probabilities of the various possible values for x, and determine, and then after you've done that, find the probability that x is less than or equal to 5. find the probability that x is between 1 and 3. Remember that I would put quotes around here to say that these are events, even around here to say that this is an event. The event that the sum is between 1 and 3. So first they want to find the probabilities for all the different possible values of x. And when you toss two dice, you can talk about the sum. And what's the smallest sum? So x is the sum, so what's the smallest that x can be? So that's here, and that's when, so the sum would be 2. So the smallest that x can be is 2, and the largest that x can be is 12. So we're going to need to figure out what's the probability that x equals 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So, we say that all of these outcomes are equally likely. Where is the event that x equals 2? Well, it's here. So this event is the event that x equals 2. Where is the event that x equals 3? Where is the event that x equals 4? So how about here? This is the event that x, the sum, is equal to 4. Where's the event that the sum is equal to 5? That's here. Oops, I didn't mean to do that, but that's there. And how about the sum that x is equal to 10? Where's that? That's here. Trying not to be too crowded here. That's x equals 10, right? Where's the event that x is equal to 7? Here. It's this longer, well, let's do it. Okay, that's, let's call that E7. Let's call this E. I'll just give these names that are suggestive of what I want them to be. This is E10, right? And so on. But it's also x is equal to 7. That's the event. The event that x is equal to 7. Okay, so we need to figure out the probabilities of each of these. So what's the probability that x is equal to 2? There's only one way that that can happen, so it's 1 out of 36. What's the probability that x can equal 3? There are two ways that that can happen, so it's 2 out of 36. What's the probability that x equals 4? There are 3 ways that that can happen, so it's 3 out of 36, and so on. So that's what they do. 1 out of 36 for x equals 2. 2 out of 36 for x equals 3. 3 out of 36 for x equals 4, and so on. Back down to 136 for x equals 12. So which sum is most likely? It's the 7. It's the one with the longest diagonal. Right? That was 7. Okay, so we've now done the first part. We figured out the probabilities for x equals each of these. Now the next part of the problem was figure out what's the probability that x is less than, or x is less than, or x is less than or equal to 5. Now again, how did they get to this plus? It's the same thing as before. Before, how did we get to plus? We said it was x equals 0, or x equals 1, or x equals 2, and it was or. And then we said or is union, and then we said union can become plus when they're mutually exclusive. And again, we have mutually exclusive here because if x equals 7, well, just you can see that, for example, x equals 10 and x equals 7 are mutually exclusive events. They don't contain any common points, common elements. So we can change union to plus. So the probability that x is less than or equal to 5 equals the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5. And we already calculated these, so we get 15 over 8. The probability that x is between 1 and 3 is, the meaning of that is that x equals 2 or x equals 3, but plus, again, we can change it to plus because they're mutually exclusive. They don't have anything in common. So it's 1 over 36 plus 2 over 36, which is 1/12. Okay, let's try another one. This one may be a tree diagram may help us. So let's look at this. Company records show that 5% of all resistors produced at a certain electronics plant are defective. Suppose that 2 resistors are picked independently from the plant's production line, and assume the random variable x denotes the number of defectives in the sample. So if we're taking 2 and x is the number of defective, then x could be 0, it could be 1, and it could be 2. Can't be anything but those 3 values. Those are the only 3 possible values. So they asked to find the probability that x equals 0, 1, 2, and also the probability that x is less than 2, assuming that resistors are picked independently. Okay, so we're going to assume that. Okay, whatever that means in terms of actually picking them, we're not thinking about that. We're just assuming that it means that we're picking them independently, and that we're saying we can use the rules about independence because we're assuming that these are independent. So, okay. And then they also do part B, find the probability that at least one of the resistors is defective at least once. We have to know what that phrase means, at least one. And find the probability that at most one, so we have to know what that phrase means. Okay. So we're going to make this kind of tree diagram. So we're going to put a dot and call it start. And then we say, okay, what are the possibilities? Well, we might get one that's not defective, or we might get one that's defective. And what's the probability that we go along this route? It's 0.95. And what's the probability that we go along this route? It's 0.05. Okay? Now, once we've gotten a non-defective here, then we say what can happen on the second pick. So again, we could get a non-defective or a defective, and again the probabilities are the same. Now, that's because we assumed independence. Like, if you only had 100 or 50 resistors and you picked one that was not defective, then the probability would change for the next pick, right? Because you take it out and you don't replace it, or if you don't replace it, then the probability would be different for the second pick, because the box would contain a different number of non-defective resistors. Okay? All right. So anyway, but we're assuming independence, so we can put 0.95 here, and we can put 0.05 here. And the same thing if we go along this path. We're assuming independence. So even though this one was defective, we still say it's 0.95, that it's not defective. So that's where the independence comes in. Now they say the outcomes may be viewed as NN, NN, ND, DN, and DD. And we have the probabilities for this outcome, this outcome, this outcome, and this outcome. These are not equally likely anymore. We're not talking about equally likely outcomes now. Where, for example, ND means that the first resistor picked was non-defective and the second was defective. Since 5% of all the resistors produced are defective, the probability of picking a defective resistor is 5%, and the probability of picking a non-defective resistor is 95%. Moreover, since we assume that the resistors are selected independently, the probability of selecting a non-defective and then a defective will be the product of 0.95 times 0.05. That is, the probability of the outcome ND is that. The probabilities of all the outcomes and the associated values of x are listed here. So we have all the outcomes, we have their probabilities given here, and then we have the x values associated with that. Remember, x is the number of defective. So how many are defective here? 1, 1, 2, 0. Okay, so what's the probability that x equals 1? There are 2 ways that x can equal 1, this way and this way. They each have probability this. They're each mutually exclusive, right? If you get this, means you got non-defective on the first and defective on the second. That's not the same as getting defective on the first, and so they're mutually exclusive. So you can add these probabilities to figure out what's the probability that x equals 1, which I guess was one of the questions. Yeah, probability that x equals 1, you add those two, you get that. Probability that x is equal to 0, that was this one here, so it's this number. And the probability that x equals 2 is this number. So you get this, this, and that. Okay. Now part B, the probability that at least one of the resistors is defective is the at least one means what? That the number is greater than or equal to 1. Now, what rule are they using? They're using the rule for finding the probability of a complement. So this is 1 minus the opposite of this. But what is the opposite of x is greater than or equal to 1? It's x equals 0. So it's 1 minus x equals 0. The probability that x equals 0 is this. Sorry, this. So it's 1 minus that. 1 minus this is that. So that's the probability that x is greater than or equal to 1, which of course is the probability that, no, not of course, anything. Sorry, that's it. The probability that at most one of the resistors is defective, so now you have to know what the meaning of at most one. So that's, now again they're using at most one, this means 1 or less, and so that's equal to the 1 minus the opposite of the probability of the opposite of that. So what's the opposite of less than or equal to 1? Equal to 2 is the only other possibility. So they put that in. We get this number.